All right. We are moving on. So we've spent all this week on the fundamental theorem of calculus. And so the last part is taking a look at a little bit more advanced, finding the derivatives of a little bit more complicated functions that have an integral in them. That's what it's all about. Plus, we're going to manipulate the things a little bit. So I'm giving you a function, f of x is equal to 3x squared plus the integral from x to 5 of the sine of t dt. Now, just from the outright, I want to make sure that you understand why is it that you have to use two separate sets of variables? Why do you have to write two separate sets of variables? Why do I have x's and then all of a sudden I have t's always in the function over here? Any guesses why we have to do that? Like, why can't I just make this an x and this an x rather than t's? You know what I mean? Why do you always have to mess it up? Stop and think about it. Don't write this down, but what if I said, find me f of, I don't know, 4. What would happen in this if we did that? Well, it would be 3 times 4 squared plus the integral from 4 to 5. Then look at what would happen here. It would be of the sine of 4 dx. Okay. That changes the problem, because now we've turned this integral into a constant, and that's bad. Okay? Because the key is that it's all about this integral in the area bounded by this curve. This ruins it right here. This is why we have to have a separate variable here in the functional part than we do in the integral part. Okay? So that's the reason why you can't just make those all the same. They have to be two separate variables. This part right here has to have a different set of variables than the other one. All right, well, let's figure this out. So I don't know, we'll just go from what we've been doing before. F prime of x, so we're finding the derivative. That's equal to 6x. That one's easy. Plus, now, the integral here. So I got to find the answer to this, and then I got to find the derivative of that. So making sure that you see the notation, what I'm going to do is I got to put that derivative symbol here, the fact that I'm going to be taking the derivative of that. But then let's just go ahead and do this thing here. So let's do the thing. Do the thing. We got to integrate the sine of x. What's the integral of the sine of x? Negative cosine. So this is the negative cosine of t evaluated from x to 5. Okay? So this becomes 6x plus, well, I'm going to hold off on that again and do this thing. So it's negative cosine of 5 minus the negative cosine of x. Okay, I just did the thing, f of b minus f of a, that's all. Okay, now it's okay for us to find the derivative here. So what's the derivative of the negative cosine of 5? 0. That's a 0. This, because cosine of 5 is just a number. Then this is plus, what's the cosine, the derivative of the cosine of x? Sine of x. Negative sine. So this made it a plus. The derivative of the cosine is a negative sine. So the final retail answer is 6x minus sine of x. Wait a second. I thought all you had to do was plug in the x into here and you get your answer. Right? That's what we've been learning. That's what we learned yesterday. We wrote a rule. Just take that variable and stick it in here and you get your answer. Say it again? Right. It's when the x is up here, that's fine to do that. And the constant is down here. Remember, it doesn't matter what the number is. Why does it make sense that this answer is the opposite of this answer? You know, the answer here is opposite of what we would have anticipated. Right. Instead of doing f of b minus f of a, we did f of a minus f of b, and that's why we ended up with the opposite. So here's a rule. Let's write a rule. Okay. The derivative of the integral from x to k of f of t dt. This is similar but different to the rule that we wrote for the second fundamental theorem of calculus. Here we're finding the derivative of the integral, but we're going from k to x of f of t dt. What is the answer to that? Say it out loud. Negative f of x is correct, because it's the opposite. And we can prove it just by walking through a generic case of that. Okay, so this is one scenario. If we flip the order of the limits and we put the variable on the bottom, this is what happens. So that's one of the advanced rules. Here's another one. What happens, again, if we were out to find f prime of x, but f of x looks like this? It's the integral of, say, 4 to x cubed of t plus 2. So what's the difference between this one and all the other ones that we've done? This thing is now a brand new function. Okay, there's a function up here rather than just an x. Okay, how do you suppose that changes what the final answer becomes, and that we can then carry this out? So by the time we're done, you're going to be able to look at this and be able to instantly tell me what the derivative is without writing anything else down. Okay? But we're going to go the long way first, because you got to do it the long way. You got to know where it comes from. All right, so let's do this. F prime of x is equal to. So it's the derivative of this thing. So it's the derivative of that. And if you don't mind, I'm going to do the thing. Okay? So I'm going to do the thing. 1/2 t plus 2t evaluated from 4 to x cubed. T squared. Thank you. So I got this. We found the derivative of both sides, and then I just did the first fundamental theorem of calculus here. So then let's just crank that thing out. Here's the derivative, and I'm going to do the thing. So I got 1/2, watch this, x cubed squared plus 2 times x cubed. So that's the first thing. That's f of b minus f of a. 1/2 times 4 squared plus 2 times 4. Okay. Everybody see what he did there? Just plug it in. Okay. So, all right, let's find the derivative. What's the derivative of 1/2 x cubed squared? Everybody agree that 1/2 x cubed squared is the same as this? Okay, so the derivative of this is 3x to the 5th. Okay, so the answer to this part is 3x to the 5th. Then plus what? 6x squared. Okay. And then the derivative of all this? 0. So the final answer is this. So that's the derivative. The derivative of this is this. Wonder if there's any other kind of correlation between this thing and what that answer is. Yeah. Yeah. Yep. Because f prime, this was the function, so therefore f prime equals this, equals this, equals this. 3x to the 5th plus 6x squared. Let me try this. I'm going to factor. We can factor something out of this, right? So what can we take out? 3x squared, which leaves us x cubed plus 2. Look at this and look at this. Looking for a pattern here. Is there anything recognizable? Yeah. Right. I'm going to watch this. I'm going to rewrite this in a much better way. I'm going to put the 3x squared on the back side. Watch this. X cubed plus 2 multiplied by 3x squared. This is the same exact answer, but it's just written a little bit differently. Is that what you got? Okay. Now, how do you suppose you can go directly to the answer of what f prime is just by looking at this? What is actually going on here? Good. What you do is you take the x cubed, plug it in for the t. That's where this came in. And then you multiply the function by the derivative of whatever the function there was. So you can write the answer, say, it's t plus 2. Okay, I plug in an x cubed, so it's x cubed plus 2. And then we multiply by the derivative of the x cubed, which is 3x squared. That ends up being the shortcut on how you handle any kind of problem with a derivative of an integral which has a function inside. Okay, so let's just do another one. And we're walking. Okay, so if I say to you, okay, here's another one. We'll do it the short way now. F prime or f of x is equal to the integral from 3 to, the sine of x times, or of the integral of the square root of t dt. Knowing that, what's the derivative? Go try to match that pattern over there and tell me what the answer is here. Once you get the handle of it, it actually is very easy. And it can always be proved using the long way. Okay, what did you get for an answer? Square root of sine of x, right? Just plug that in, multiplied by cosine of x. That's the derivative of that function. Okay? And we can prove it using the long way. It'll always work. Okay? Okay. So, let's write that rule. Back to the back. What would this look like here? Well, I'll do the setup. The derivative with respect to x of the integral from k to f of x of g of t dt. Look at that careful, that setup. This is the general rule for this scenario. Okay. Yes, ma'am. Perfect. G of f of x times f prime of x. Okay. That's the general rule. Now you handle it. It's just what we did in number 2 and number 3. Okay. All right. Another scenario. So what happens if we got something like this? F of x is equal to the integral from x to, say, x plus 4 of t plus 2 dt. Okay, you see what's different here now, right? Now there's a variable in this one. We got x here, and then we got a function here. Okay, all right, you do the thing. You go do it. I'll go do it. We'll see if we come up with the same thing. Do the answer, follow the same thing we've been doing all along, and plug everything in, see what happens. Okay, do we agree on our work? Do we agree? Anything? So the deal was we had to plug in this one, and we had to plug in this one, and then this time when we took the derivative, there weren't any zeros, because there weren't any constants like the other one. So that's why we ended up with the derivative of this thing, I just left it here. The derivative of this thing, I just left it here. Okay? And then, well, look at that, it just kind of subtracts off, and we get 4. Okay, so I suppose if I give you a new one, and I say f of x is equal to the integral from x to x minus 5 of t plus 3 dt, and I say what's f prime of x? Is the answer -5? Go prove it. It's going to take you 1 minute. Go do it. And then maybe we can explain why. Because that's where the fun begins. Anybody get it to work out? Does anybody have an explanation for this? Okay, Kayla, you keep going. And I wonder if this works in all cases. Or if this is the only scenario that it works. And you know where we're going next. Okay, Gunnar, you got something for this? Yeah. Number 5, I mean. Number 5. What do you got? Okay.
Is it the sine of x minus x cubed?
Oh, for this one? I don't know. We didn't get there yet.
Oh, I thought that's what
in this one here, do you see how this is x plus 4? That's what we had in here, and I plugged it in. It was this one plus this one. This plus 2 minus this plus 2. See the connection? We plug in this one into here. Boom. Minus, we plug this one into there. Boom. Okay? So, the fact that it's 4 is actually dependent on the fact that this is linear. Okay? If it's not linear, then some weird stuff happens. Okay? It doesn't always turn out like that. All right, so we've got this thing here. Phew. I wonder if we can make a prediction as to what this answer is just based on the fact that there's clearly a chain rule thing going on here, right? And recognize a possible pattern with how we plug things in. Any suggestions as to what the derivative of this wacky function is? Any ideas? Without doing the work. Stop and think about how everything else has played out over all of the lesson today. How we did a substitution, we did a derivative. Yes? You gonna try it? Okay, so plug in b where? Plug in the sine of x into t? Okay, so the sine of x plus 2 times the cosine. Keep going. Minus x cubed plus 2 times 3x squared. 2x squared. No, 3x squared. Okay? So wait a second. That means that we can answer this rule. Rule number 3. What would be the derivative, okay, here we go, of the integral from f of x to g of x of, I'll use w of t dt. This is then now the most complicated scenario we could get. Okay, write the other half to this. Okay, Kayla, word for word. Hang on. Did you get that? Okay, that's the general form. We can prove that it works for every single scenario. Okay, that's going to do it for today. Now, I'm going to be gone tomorrow. So, what I have is practice sheets. Kind of a summary of the last 4 sections. Okay? So, you're going to get 3 worksheets. I'd recommend just stapling them all together. And they're going to be due on Monday, but you should be able to get through almost all of them on Friday. And I want you to collaborate. I want you to talk to each other. And take them all and staple them. You can take them now, I guess, if you wanted to. He's just going to be gone. Or you could take them tomorrow.